Some properties of the integral. So, if you have an integral that is like, I don't know, 1 to 7 of, x squared plus 1 dx, if for some reason you want to switch the 7 and the 1, okay, you can do so. But it introduces a negative sign in front. It changes the sign of your final answer. 2. If you integrate from, say, 72, whatever, 72 to 72 of any function, plus edx, whatever, okay, this is going to give 0. So you can break this down in terms of the limit of a Riemann sum, but I think intuitively, from the notion of area, well, there is no area. So it's not surprising that we get 0. Constant function. If you have a constant function, say you have the integral of, say, -3 dx from 2 to 5. Well, what's happening here? If I draw a little picture, and I have, say, 4 here, and then I got that, and then I have this, and then I extend this, and oh yes, very good. And a little bit more over here. Okay, so we're going from 2 to 5, and our function is -3, so it's a constant function, a horizontal line. Horizontal line going like this. And we're going from 2 to 5. So we get this area here. It's going to be, as we've seen, negative a1. So negative of 3 times 5. And we're going to think of this as -3 times 5. So what do we get? We get the constant, and then we get b minus a. Oops, made a mistake. My mistake was, this isn't 5. This isn't 5. This is my base. My 3 times 5 is wrong. This should be 5 minus 2. So sorry about that. This should be 3 as well. So what you get every time is you get this rectangle, and the sign will be positive or negative, depending on whether the constant is positive or negative. So in general, you get the integral of a constant function from a to b. Dx is going to be k times b minus a. Okay, sum. The sum is straightforward. If I'm doing integral from 2 to 4 of a function plus a function, okay, you can distribute the integral sign the same way you would distribute a sigma. constant multiple. If I have, say, 7 times, say, x squared dx, okay, this constant multiple can move out front. So, okay, one can prove all these properties from the definition, but we're mostly just going to use them. Difference is just like sum. You know, if you have a difference of functions, it's a 9, then you can distribute your integral notation like so. Okay, one last property to talk about. Seven. If I want to do an integral from 1 to 6 of a function, and let's say I'm going to add an integral from 6 to 11. Then these can be brought together in a single integral. So this guy goes from 1 to 6. This guy goes from 6 to 11. You can bring these together into a single integral, like so. In general, if you have the integral from a to b, a to c of a function dx plus the integral from c to b f of x dx, then these can be combined into a single integral from a to b f of x dx, where we're assuming a is less than b, and c is actually any real number. You don't have to insist. You may think, oh, I need to insist that c is between a and b, but it turns out you do not. Okay, you may say, well, I need to have a here, I need to have b here, and I need to have c here to make my integral work, because I'm going to integrate like this, and then I'm going to integrate like this, and thus I will get the whole thing. But if you think about it, if I have instead a b and maybe my c is over here, let's get our formula here. So looking at this formula, it's still going to work. I can motivate it here. You can say, if I want to go from if I go from a to c, like that, and then I go from c to b, oops, if I go from c to b, what's happened? Well, I have indeed gone from a to b. Okay, the purples add up to the green. I don't need c to be between a and b. Okay, let's do an example to illustrate some of these. Pause and copy, pause and copy, pause and copy. Okay, 1. I'm going to demonstrate that this guy does indeed equal 38. So let's just recopy to begin with for f of x plus 3 dx. So we saw above that the integral can distribute across a sum. put some brackets in here just to clean it up a little bit. And then we get 1 to 3 dx, so I can distribute across the sum. Next, the 4 here can move out front. And now, the integral from 1 to 3 is given to be 8. So we got 4 times 8. Now my second integral, this is a constant, so remember it's going to be, so it's going to equal k times b minus a. So what we decided above, so I'm going to get k times b minus a. So I get 32 plus 6 is the 38 I was expecting. Okay, number 2. Number 2, I want to make this one a little bit more fun. So my apologies. I'm going to make a little change here. I want to rearrange. Let's rearrange the 1 and the 5. Let's just swap those two. So how am I going to do this? So first of all, white them out. So the 1 and the 5 are going to switch because it's more fun, and we like fun, don't we? We're not allergic to fun. So number 2 here. Recopy f of x and dx. So I want to use the information given. So I have the integral from 1 to 3, and I have the integral from 3 to 5. Here I have smaller number and bigger number, and likewise here, smaller number and then bigger number on top. So why don't I rearrange this so that the smaller number is on the bottom? Hopefully you can see why I would be motivated to do that. So I can change the 1 and the 5, but I have to stick a minus in front. That was one of the first properties we looked at above. So now I have minus the integral from 1 to 5. Well, I'm not given the integral from 1 to 5, but I can break it up into an integral from 1 to 3 and an integral 3 to 5. So it'll be minus, bracket, integral from 1 to 3, plus integral from 3 to 5. Now these two values are given. First one is an 8, second one is minus 3. So overall, I get minus 5. So one last thing about integrals. The notation, I want to say something about the notation. Okay, where does it come from? Well, kind of, very roughly speaking, the sigma in the formula so it may be helpful for you to think of this as becoming a kind of a different kind of sigma. We use this, our integral sign, and this guy is going to become dx. So delta x is a reasonably sized chunk of x, and dx is meant to invoke what's called an infinitesimally small piece of x. And then this guy becomes f of x, and overall we get integral f of x dx. So just to give you something to hold on to there, to see where this new notation has its roots.